So continue, right? Standing waves in a string. So we said, there are only those waves which has the wavelength that is the multiple of what? Lambda m equal to 2L by m, multiple of this wavelength. They are the only wave that are allowed to that corresponds to production of standing waves, okay? Which means we also looked at there are only certain frequencies which are allowed, right, or which are formed when we have these standing waves, right? We looked at that also. And then we said, okay, so these, standing waves, they kind of form a series of the waves. If you note, let us see, where is my equation? So what we said, if m equal to what? M times b over 2L. So if we look at this, here, what happens is really the frequency, every frequency, right, they are actually just the multiple of the first frequency, right? So we have, let's say, f1 equal to what? M times b over 2L, f2 equal to what? 2 times of this first f1, and then f3 equals what? 3 times of m equal to 3, and then this part remains same. This is just f1, right? So you see, these frequencies, they form a series of frequencies, right? So f1, f2, f3, kind of, they have us, they are just really one, like they're like this 1, 2, 3, dot dot dot, right? Like, so they just form a series of harmonics, okay? That's when we have a standing wave in a string, it can, produce a series of harmonics, okay? However, this is not always the case in all the sound producing or the, standing wave producing instrument or equipment or any physical object, okay? So there is a relationship between the, if you look at the frequency spectrum, there is a relationship between the frequency and the relative amplitude. So if we have here, the frequency is here, this is 1000 hertz here, the relative amplitude, the maximum is 1, okay? And then if you look at the frequency here, first fundamental harmonics, right? First harmonic has like maximum almost 1, little bit lesser than 1, right, relative amplitude. Once we get to the overtones, it means higher order harmonics. The frequencies are kind of, as you increase the frequency, right, as you increase the frequency, the amplitude is going to go down. And then as we increase the frequency, amplitude are going to go significantly down. It kind of almost looks like, going exponentially down, okay? So that's the frequency spectrum. So as we go towards the higher order harmonics, the relative amplitude is going to go down. Now, where do we use, all these things? We looked at, standing wave in a string. Where are these helpful? Or where are these useful in real life? You guys are all familiar, right? Like, a string, so that is a string. Guitar has a string, so it must be used there too, right? So yes, actually, yes, this is an instrument which uses, a string, like a guitar, violin, these, etc. These actually function under this principle of a standing wave in a string. Why do you think, why do you think we are able to produce different varieties of sound from, just one of these string in a guitar? If you place, the same string, if you, put your finger, I don't know what it is called, whatever you, put, press it, like, press it, it can produce a variety of sound, right? So why is it happening, really, right? What you are doing when you are pressing, a string? You're really changing the length, right? If you change the length, what happens? You can also change the wavelength, and then you can also change the frequency, right? So you will be able to hear varieties of sound from just one string, just pressing at a different position. Okay? Now, what do you think would happen if we, you know, if we superimpose two waves of different frequency? What do you think would happen? So let's look at this here. So superposition of a wave here. We have a wave. Look at this. One is this blue colored wave that has a higher frequency, right? More wiggles here, more cycle per second, and then we have this other frequency here, right? Like, I mean, other wave, the red color wave here, which has a smaller frequency. Okay, so what happens when they superimpose? That's just really like saying both of these are cos function, right? It starts somewhere here. So this is like really 2 cos x plus cos 5x, right? What happens if we have that? Well, even if we were to do this mathematically, it becomes more complicated. Really, it's no longer, you know, just cosine or sine function. Okay, so this is really, it gets more complicated. It will form, the result is more, you know, it's a complicated periodic function. This is again periodic, but then it's not a simple sine or cosine function. Okay, so you see here, right? You got all complicated equation. So we see this superimposition of the waves of different frequency. For example, let's look at, like, you know, in the case of I think you guys cannot see this here clearly, so I'm going to bring it closer to you guys. Okay, so this is for flute. You see this, it's periodic, but it's not just simple sine and cosine. This is for clarinet, this is for trumpet, you see, and then there are some of these others for violin, here is for piano, and then so quality of the note actually depends on number of overtones, right? So higher order harmonics and their relative intensities, okay? So we saw that superimposition of the, you know, two waves with different frequencies give rise to more complicated wave, right? I mean, complicated periodic function. Now, we also talk about the standing wave in the string, and then we see we can get the, you know, harmonic series, right? Harmonic series of frequencies. But do you think it is true in, you know, some other instrument like a drum or, you know, something like that? So let's say here is a, you know, standing wave on timpani drum. Timpani drum, I don't know how to say this. Timpani drum. Okay, so here is just the figure here. So in this drum you can, you know, if you beat it, right, you can produce the sound, but then, and you can actually have a standing wave, but does it give rise to the harmonic series? That's the question. So it turns out that actually it's like this here. See, F1 is like that, and then, you know, this is it can get more complicated. So actually, so you can actually look at the nice animation. Okay, not whole detail, but look at the nice animation. I'll post the link in the lecture overhead, so you guys will be able to see what is happening here. This is, I think, difficult to see here in the picture. In the animation you see actual movement. Okay, so here it turns out that actually these standing waves on the drum head, this, you know, they don't actually, they do not, you know, the frequencies of oscillation, they don't form harmonics. Okay, so they don't form harmonic series, so that's the difference here. But then, oh, so yes, so this is the website I have here, animation of standing waves. It's from PSU, you know, so you can look at this link here. It has a really nice animation. Okay, please actually go ahead and then look at your, you know, lecture overhead, and then go to this link and look at this before you proceed for next part of the video. So take some time to look at it, you know, just scan through that animation, and then we'll continue here. Okay.